Hey guys, welcome to today's Speed Forces, Lead Code post contest discussion, right? We'll be discussing 4 problems, and today's contest was relatively easier than the previous problems. So let's get started. So, what does the first problem say? Let's have a look. It's called Special Array 1. An array is considered special if every pair of its adjacent elements contains two numbers with different parity. You are given an array of integer nums. Return true if nums1 is a special array, otherwise return false. Okay, guys. So this is a very straightforward problem, right? What does this say? You are given an array, and what do you need to check? That no adjacent elements, right, have the same parity. Same parity, right? Now, what are adjacent elements, guys? If nums of I, right, is the ith position in your array, then what is adjacent to it? We have nums of I minus 1 and we have nums of I plus 1, right? These are the adjacent elements. So basically, if this is my array, okay, these are my elements. What do I need to do? Let me choose another color, right? I need to check that do these have the same parity or not? Do these two elements have the same parity or not? Do these two have the same parity or not? Do these two have the same parity or not? And so on and so forth. Okay. So basically, when I am at index I, either I can check for index I plus 1 or I can choose for index I minus 1, because this will stay constant. If you're at I and you're checking for I plus 1, you will check this, 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 and so on and so forth. But if you're at I and you're checking for I minus 1, you'll start over here and then you'll check backwards. Okay. So the code for this is very simple. Speaking about the time complexity, the time complexity is big O of n because we'll be iterating over adjacent elements and there are n pairs, right? And the space complexity is O of 1 because we won't be using any extra additional space. Let me use some other color and let's move on to the implementation. Very simple implementation. First, we have bool OK, which is true. Now, I am iterating from 1 to nums.size. And at every index, I am checking current index parity with the previous index parity. The thing is, OK will only stay true if nums I modulo 2 is not equal to nums I minus 1 modulo 2. There will be this here as well, right? Otherwise, this will become false. Basically, what I'm trying to say is, you can write this as well. If nums I modulo 2 is equal to nums I minus 1 modulo 2, then OK is equal to false, right? Instead of writing this, you can do this as well. But this is a very neat trick. Instead of writing if else, you can write this. What does this do? This ands OK with this condition. Basically, if both parities are not the same, this will return a 1 and then this will be ANDed with 1. So at any case, for example, 2 and 2, okay, this will return 0 and then OK will become 0. And no matter what you AND OK with, it will still remain 0. And in the end, you return OK. So that is more or less for the first problem, guys. Moving on to the next problem. A very neat problem. Let's have a look on how to solve it. Special array 2. An array is considered special if every pair of its adjacent elements contains two numbers with different parity. You are given an array of integer nums and a 2D matrix query, where queries I has from I and to I. Your task is to check that the subarray nums from I to I is special or not. And it is special if all pairs of adjacent elements have different parity. Return an array of Boolean answers such that answer I is true from so on and so forth. Okay. So what does the problem say, guys? Let's have a look. We are given an array. Okay. Let's consider that the array is 1, 1, 2, 4, 5, 6. Okay. Now, along with this array, we are given some queries. Okay. Sorry for the spelling mistake. What are these queries? Each query is of type L2R. Okay. This is L1R1. This is L2R2. Right. So on and so forth. Up to LQRQ. For each query, we want to know that is the subarray, basically is ARR, LI to RI special or not. Okay. We just discussed how to check if ARR, LI to RI is special or not. And what is the basic idea of checking if something is special or not? An array is only special. Keep in mind, guys, okay? Is only special if ARRI modulo 2, okay, not equal to ARRI plus 1 modulo 2 for all indices in range L to R minus 1. Why am I saying this, guys? Let's have a look. For example, we have this array, right? 1, 1, 2, 4, 5, 6. Okay. 1, 1, 2, 4, 5, 6. Let's consider that my query is 1 to 2. Okay. So this is my query. So this is index 0. This is 1, 2, 3, 4, 5. Right. Now, I am at index 1. Index 1 parity is not equal to index 2 parity. So it is fine. Now, when we are at index 2, are we going to check it with index 3's parity? No, because it is not in the range. So this condition right here, that ARR I modulo 2 is not equal to ARR I plus 1 modulo 2, you only need to check from the range L to R minus 1. As simple as that. Is this much clear, guys? Does this make sense? That we don't need to check for this condition. What condition? ARR I modulo 2 not equal to ARR I plus 1 modulo 2. I don't need to check this condition in the entire range. I just need to check this condition in the range L to R minus 1. Because when we are at the last index, I plus 1 goes outside the bounds. Okay. So this is the first observation, guys. This is how we check if an array is special or not. Now, the second thing is, how do we go about solving this problem? Because if we run a simple for loop, okay, worst case, each query, let me write this down, guys. First case, each query is of type 0 to n minus 1. Yes or no, guys? Worst case, what is the largest range possible? 0 to n minus 1. And if we do a brute force, that is iterate from L to R minus 1 for each query, it is worst case O of n per query. Yes or no? Now, If it is first case O of n per query, our time complexity will be O of n into Q, where Q is the number of queries and n is the size of the array. Since both here are 10 raised to 5, right? N comma Q, both are smaller than equal to 10 raised to 5. This will be around 10 raised to 10 operations, which will result in a TLE. Okay. Is this much clear, guys? If we try to do O of n per query, we will have 10 raised to 10 operations, which will result in a TLE. So how do we optimize this? What can I do, guys? A very simple thing. Let me write down the array again. 1, 1, 2, 4, 5, 6, right? I have been given a query L to R. What do I need to know? I need to know that in range L to R minus 1, does there exist? Let me write it down, guys. Does there exist such an index where ARR I modulo 2 is equal to ARR I plus 1 modulo 2? Okay. In which range? In range L to R minus 1. If there does exist such an index in range L to R minus 1, where ARR I modulo 2 is equal to ARR I plus 1 modulo 2, we will return false. Otherwise, we will return true. Yes or no, guys? If it does exist, then we'll return false. Otherwise, we'll return true. Now, how do we maintain this? This is a very good technique to learn. So if you didn't think about this during contest, pay attention. The idea here is we are going to use prefix sums. Okay. And how are we going to use prefix sums? Okay. For using prefix sums, wherever ARR I modulo 2 is equal to ARR I plus 1 modulo 2 in our array, let's say same array, okay, we are going to store prefix of I is equal to 1. Basically stating that at this particular index, this occurs. After that, what we are going to do, we are going to generate the prefix sum table. Basically doing prefix of I plus equal to prefix of I minus 1. Now, how will this help us? Let's have a look. We are going to use prefix sums, right? To calculate this. How are we going to use prefix sum? Let's have a look. So my array is 1, 1, 2, 4, 5, 6. Okay. Now let's generate my prefix sum table. What did I say? Wherever ARR I modulo 2 is equal to ARR I plus 1 modulo 2, my prefix I is going to be 1. So at index 0, are both parity same? Yes. So it is going to be 1. Here, is it same? No. So it is going to be 0. At index 2, is it same with index 3? Yes. So it is going to be 1. Here it is going to be 0. Here it is going to be 0. And here, of course, it is going to be 0. Now, let's take prefix sum over this table. If we take prefix sum over this table, we will get 1, 1, 2, 2, 2, and 2, right? What does this prefix sum table signify? Prefix of I denotes the number of indices in range 0 to I such that ARR I modulo 2 is equal to ARR I plus 1 modulo 2. I hope this much is clear, guys. Okay, we generated this table and then we took prefix sums over this table. Let me erase this for now and let me show you how we can use this to process queries. Okay. Now for a given query, let's say the query is 1, 2, right? For this query, what did we need to check, guys? Is there any index in the range L, R minus 1 such that ARR I modulo 2 is equal to ARR I plus 1 modulo 2? So if we just do that over the prefix table, how do we generate the sum of prefix table in this range? Isn't it just prefix of R minus 1 minus prefix of L minus 1? Since this is the range I want the sum over, isn't this going to be the formula? So when it is 1 and 2, this is going to be prefix of 0. No, prefix of 1 because R minus 1 will be 1 and minus prefix of L minus 1, which is prefix of 0. Okay. Now, what is prefix of 1? It is 1, guys. What is prefix of 0? It is 1 again. This is 0. What does this mean? It means that there are no indices in range L to R minus 1 such that ARR I modulo 2 is equal to ARR I plus 1 modulo 2. Does this make sense, guys? But now let's take a case where the answer is no. So here we return true. Okay. Now let's take a case where the answer is no. Let's take a query. Okay. Let me write it down here. Let's take a query where the answer is going to be no. Let's say 2, 3. Right? So what prefix sum do we need? We want the sum in range 2, 2. Right? So what will this be? This will be prefix of 2 minus prefix of 1. This is nothing but 2 minus 1, which is 1. You can see this is not 0. It means that there exists an index such that ARR I modulo 2 is equal to ARR I plus 1 modulo 2. And here we return false. Is this clear, guys? We are storing all those indices such that ARR I modulo 2 is equal to ARR I plus 1 modulo 2. And then by getting the sum over a range, we are able to identify that are there any indices that satisfy the constraint we want, or are there no indices? Looking at the time complexity of this, to generate the prefix table, we are going to need O of n time. And to answer each query, we are going to need O of q time. So our overall time complexity is going to be O of n plus q because we don't really know which is the larger one, right? Right? So our time complexity is O of n plus q, and our space complexity is also O of n plus q because we are going to need a prefix sum table and we are going to need to return the answer in a vector, right? Basically, for each query, we are going to need to return its answer in a vector. So that is the extra space we'll be using. So we have a vector bool answers, which is initially 1. Okay. I'm going to set it to 0 whenever our constraint is satisfied. If nums I modulo 2 is equal to nums I plus 1 modulo 2, prefix of I plus equal to 1, and then prefix of I plus 1 plus equal to prefix I. This is basically generating the prefix sum table. You can do it using 2 for loops as well. I'm just doing it in 1 for loop. Then I'm iterating over the queries. I have left, I have right. In left, you have queries I0. In right, you have queries I1. Number of bads. Number of bads is the number of indices that don't follow our constraint. So if right is greater than equal to 1, because we are trying to access right minus 1, right? So we don't really want this to become minus 1. So if right is greater than 0, then it is prefix of right minus 1, else it is 0. Similarly, if left is greater than 0, then it is prefix of left minus 1, otherwise it is 0. Then if number of bads is greater than 0, then answer of I is equal to 0, else answer of I is equal to 1. But I have already set it to 1, so I don't need to write the else condition. Then I return answer. A very simple and a very clean code. You can have a look, right? Let me give you a minute or so to have a look at the solution. Okay. So guys, moving on to the next problem. If this one is clear, right? Sum of digit differences. This is actually a very neat or a very good problem, right? It teaches the importance of mathematics and seems to be one of my favorite problems of this problem set. Sum of digit differences of all pairs. You are given an array nums consisting of positive integers where all integers have the same number of digits. Okay. The digit difference between two integers is the count of different digits that are in the same position in the two integers. Return the sum of digit differences between all pairs of integers in nums. Okay. So what does this say, guys? So we have 13, 23, and 12. Okay. So let me write down 13, 23, and 12. We are given an array. Okay. And we are said that we have n integers such that each number has the same amount of digits. Okay. Here, each number has 2 digits. Now, for each pair of numbers, we have to calculate the number of positions where the digits are different. Basically, let's name that f of x comma y denotes the number of positions I such that xi not equal to yi. Okay. So what do we basically need to calculate? We need to calculate f of 13 comma 23 plus f of 23 comma 12 plus f of 13 comma 12. Okay. I'm just mathematically defining what function we have and what do we need to calculate. Our answer is this. Now, in how many positions does 13 and 23 differ in? It differs in only one position. So it is 1 plus 23 and 12 differ in two positions. So 2 and 13 and 12 differ in one position, that is 3 and 2. So 1. So the answer here is 4. Let's have a look, guys. Is the answer 4 in this case? Yes, the answer is 4 in this case. Okay. So what are some observations here and how do we go about solving this question? Okay. Guys, the main observation here is that the positions are independent of each other. What do I mean to say, guys? Let's say my number is 13 and my number is 23. Okay. This number being 3 does not affect this row, or let's say there was another row which was 5, 5. It does not affect this row or any row after that or before that. So basically, this row or this column, you can say this position is independent. Even this position is independent and this position is independent. Okay. So if I am able to calculate this separately also, right, then I can add them and find the answer. Here it is 0 plus 1 plus 0, which is 1. And 512 and 523 are different in exactly one position. Okay. Now, what did we realize, guys? We realized that the positions are independent to each other. So can I say that this 13, 23 and 12 can be broken down into two separate columns, okay, which is 332, 1 to 1. And then if we are able to find the answer for this separately, let's say this is X, if we are able to find the answer for this separately, which is Y, won't our final answer be X plus Y? Let's have a look, guys. For 3, 3, 2, 3 and 3 don't differ. This 3 and 2 differ. This 3 and 2 differ. So the answer for this row is 2. Now for 1, 2 and 1, 1 and 2 differ. 1 and 2 differ. 1 and 1 don't differ. So it is 2. So what is our final answer? It is just 2 plus 2, which is 4. Does it make sense, guys? If we can process each digit separately, we will find our answer. This is the first observation that I want you all to consider. What is that observation? That positions are independent of each other. Okay. Now, how do we go about calculating this answer? Because even if we have something like 13, 23, and 12, and we are going digit by digit and calculating the answer, it is not really simple. Why? Because there are NC2 pairs. Why are there NC2 pairs, guys? I have n numbers here or n digits here, and I want the answer for every single pair. Now, how many pairs can there exist? There are n numbers. I have to choose 2, which is NC2, which is just n into n minus 1 divided by 2 pairs. Here, n is smaller than equal to 10 raised to 5. So the number of pairs that can be generated is smaller than equal to 10 raised to 10. Okay, around that number. Now, it is clear that we cannot really do a brute force. Okay, brute force won't work. It will TLE. So what do we do here? If we can't do brute force, what do we do? Guys, we are going to use a mathematical technique today. What is it? Number of pairs. Be with me, guys. Number of pairs where, let's say, AI and AJ differ. Okay, we are talking about a single row right now in 13, 23, and 12. Let's say we are considering this row and we want to calculate the number of pairs where AI and AJ differ. Is equal to total pairs minus number of pairs where they don't differ. Yes or no, guys? I want to find the number of pairs where they differ. Isn't it the same as saying total number of pairs minus the number of pairs where they don't differ? Basically, I have three, I have three, I have two. What are the pairs? 3, 3, 3, 2, and 3, 2. Okay. The number of pairs here are 3, and the number of pairs where the numbers don't differ is 1. So can we say that the number of pairs where they do differ is 2? Yes or no? Very much possible. Makes sense. Take a minute to understand this formula. Okay. And why does this work? Because number of pairs where they differ and number of pairs where they don't differ, if you add it, you get total number of pairs. So I'm just shifting it and I get my formula. So for a particular digit row, what do I need to do? I need to calculate this. And this thing right here can be calculated very, very easily. How? Let's have a look. Now, let's consider my current digits are 5, 5, 3, 2, 1, and let's say 7, 7, 7. Okay. How many total number of pairs are there? What is n here? 1, 2, 3, 4, 5, 6, 7, 8. Okay. So it is 8 into 7 by 2. These are the total number of pairs. Okay. From this, we need to subtract the pairs that have the same digit. We can see this 5, 5 will give us the same digit. This 7, 7 will give us the same digit. This 7, 7 will give us the same digit. And this 7, 7 will give us the same digit. But how do we do this? Let me write down, okay, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, okay? How many times does 0 occur, guys? 0 times. How many occur? How many times does 1 occur? 1 time. How many times does 2 occurs? 1. 3 ones, 4, 0. 5 twice, 0, 3, 0, 0. Okay. How many pairs can we make using the number 5? We can make 1 pair. How many pairs can we make using 7? We can make 3 pairs. Yes. Okay. Now, guys, you might be thinking that, okay, I have the frequency. How do I get the number of pairs? Again, if this number right here is x, isn't the number of pairs just xc2 or x into x minus 1 by 2? Yes or no, guys? Tell me. So what do? I have been given a particular row, right? I calculate the frequency of every element, right? Now, since I have calculated the frequency of every element, I know what is my total. My total is n into n minus 1 by 2. Okay. From that, I subtract the pairs. I iterate from I is equal to 0 to I is equal to 9. And what do I subtract? I subtract the frequency of I into frequency of I minus 1 divided by 2. What does this give me? The number of pairs I can make using this digit. For 0, it is going to be 0. For 1, it is going to be 0, 0, 0. For 2, it is going to be 1 because 2 into 1 divided by 2 is 1. For 3, it is going to be 3 because 3 into 2 divided by 2. And for everything else, it is 0. So this is the formula that we come up with. So what did we discuss, guys? First, we can process each position separately. Okay, each position separately. And second, we need to apply this formula to get answer of each position. So in this example, which is 23, 13, and 12, how do we do this? We first process for this. Okay, how many pairs are there? There are 3 into 2 divided by 2 pairs. So there are 3 pairs total, minus how many are same? Frequency of 3 is 2. So that is 2 into 1 divided by 2, which is 1. So this will give us the answer 2. This will give us 0 because frequency of 2 is 1. So 1 into 0 by 2 is 0. Now, if we process for this one, the total number of pairs are 3. And how many are there with the same digit? How many pairs with the same digit? Again, here only 1 comma 1 is there, which is 1. So this is 2. What is our final answer? 2 plus 2, which is 4. I hope this is clear, guys. Now, how did I implement it? Again, we could do, as I said, right? We could iterate over the digits, which is the first position, second position, third position, fourth position, and do this. However, during the contest, I was in a bit of hurry. So I used a map to do this. How did I use a map to do this? We have the numbers 2 and 3. This is the 0th position. This is the first position. So in the map, what am I storing? Map of 3, 0. Okay. I'm doing map of 3, 0 plus plus, denoting that the number 3 at position 0 has occurred one more time. Similarly, I am doing it for 2. Now, how does this help me? When I am at this particular number, let me show you. When I am here, it does map of 3, 0 plus plus. Similarly, when I am here, it again does map of 3, 0 plus plus. So in the final map, if you look at map of 3, 0, okay, it is going to be 2. Why? Because at position 0, there are 2 numbers that have 3 in it. Okay, makes sense? So that is all that I'm doing. It helps me implement things faster, right? So here is the solution. I have a map of pair int comma int, and the frequency is in long because the answer is expected in long. It can be very large, right? Now, the number of digits we require. So for auto X in nums, what am I doing? I think we can do it without this as well, but I just preferred to do it. Currently, I am at index 0. While X greater than 0, let me just write down X greater than 0. M of X modulo 10 index plus plus, basically the number and at what position it is at, I'm doing plus plus. Now, while going to the next number, I am doing X divided by equal to 10 and I'm doing index plus plus. This is just iterating over all the digits and I'm incrementally increasing the index. After that, I want to store how many how many digits there were in the number. So I'm just doing digits equal to index because at the end, index is going to be the number of digits in the number. Okay. So initially, I'm setting the answer to nums.size into nums.size minus 1 divided by 2 into digits. Now, let me explain that as well. Basically, I am processing for every digit, right? Let me just change the color. For 13, 23, and 12, I'll be processing for this, processing for this. So for this, first we will do n into n minus 1 by 2. And let's say there is the answer for this, the number of same pairs is x. And similarly, for this particular column, it is again going to be n into n minus 1 divided by 2 minus, let's say the number of same pairs is y. So if you see the amount of times the number of digits has come, that many times we'll be adding. Okay, there is a plus here. That many times we'll be adding n into n minus 1 by 2. So initially, I'm just setting my answer to n into n minus 1 by 2 into the number of digits that are there, because that many times we'll be adding it in our final answer. Then I just iterate over my key value pairs, and the value is basically the number of the frequency of that element, right? So I will just subtract j into j minus 1 by 2 because I can make that many pairs. In the end, I just return answer. A very simple trick, okay? A math-based question, very, very simple and instructive. If you didn't know how to solve this, I hope you have understood, right? Great. Now moving on to a very easy D, okay? Like maybe it is not standard for many people, but it is a very well known trick, okay? And today we'll be learning that trick. Find the number of pairs to reach the kth stair. You are given a non-negative integer k. There exists a staircase with an infinite number of stairs, with the lowest stair numbered 0. Alice has integer jump, which is initially 0. She starts on staircase 1 and wants to reach staircase k using any number of operations. If she is on staircase I in one operation, she can go down to either staircase I minus 1. This operation cannot be used consecutively, or go up to the staircase I plus 2 raised to jump, and then jump becomes jump plus 1. Okay. So guys, let's have a look on what the problem statement has to say. Alice, okay, has been given a number k. It means that first of all, there are infinite stairs, okay, so on and so forth. There is 0, there is 1, so on and so forth. There is k, and it goes ahead. Initially, Alice is on stair 1, and she has a variable jump which is set to 0, right? Now, guys, let's say Alice is at a particular stair. Okay, Alice is at stair X. Let me write it down. Alice is at stair X. Okay, what choices does Alice have? Either Alice can go to stair X minus 1. Okay, now Alice can only do this if on the previous step, okay, on the previous step, you didn't go back. Basically, if Alice is on step 3 and she went to step 2 right now, in the next step, she cannot go back to 1. So basically, on the previous step, if you went back, then currently you cannot go back. Make sense? Great. Or what can Alice do? Alice can go to X plus 2 raised to jump. And then what will Alice do? Jump plus equal to 1. Okay. This is what Alice is going to do. The thing to notice is that we can solve this, first of all, using recursion. How do we solve this using recursion? Okay. Let's say, first I will tell you the recursive solution, and then of course we'll be looking at memoizing it. So the crux of this solution is just dynamic programming. And I will prove to you also why this works. First, we will look at the solution and then we will understand why it does not give a TLE. Okay. So what am I trying to say? For any dynamic programming solution, guys, the first thing that you need to consider is that we need to define the states. We need to define the states. Okay. And after that, what do we need to do? We need to define the transition. Right? Okay. Now, guys, what are we expected to count? We are expected to count the number of ways to reach stair K. Okay. Now, a simple observation, guys. Simple observation. Let's say I am at staircase K plus 2. Okay. I am at staircase K plus 2. And let's say jump is 0. Let's say you didn't take any jumps. Okay. It's the minimum possible. Jump is 0. I want to go to staircase K. So I will go behind. So I will go to K minus 1. Jump is 0. Now I cannot, K plus 1, sorry. Now I cannot go back to K because I have already done this step. So let's say I go to K plus jump. Jump is 0. So it will be K plus 2 again. And jump will become 1. Okay. Now let's say I want to go back. I will go back again to K plus 1 and jump is 1. But I can never ever go back to staircase K. So what is the kind of base condition right here? If I am on index or basically staircase number, which is greater than equal to K plus 2, then it is not possible. Okay. This is something that I wanted to tell you guys before moving on to our dynamic programming solution. Okay. This is a base case. Right. Now, moving on to defining our states. Now, guys, let's say I am at a particular stair. I'm going to teach you all how to come up with our dynamic programming solution. I am at stair I. Okay. What choices do I have? Either I can go to I plus 2 raised to jump. Okay. Or I can go to I minus 1. So if I am at a stair, to know what choices I have, and only if on the previous move I didn't go back. Right? So if I am on a stair, to know what choices I am going to have, what do I need, guys? First of all, I need to store which index I am on. So one of the states is going to be current stair. Okay. Or I. Second thing, we need to store this jump as well. Yes or no, guys? Because after we do this move, our jump increases by 1. And it might be that we can reach several stairs with the same jump or the same stair with several jumps. So we need to store jump as well. Okay. And apart from jump, this transition is done. For this transition, I can only go to current stair minus 1 if I didn't go back the last move. So I also need to store did I go back. Okay. Now, since these are the only things we require, now do we require anything else? No. Like I know where I am on. I know what choices I have. Okay. So what can I say? dp of current stair jump did I go back denotes the number of ways to reach stair k from stair current stair. Okay. Stair with these two constraints, with jump equal to this and did I go back equal to this, right? I hope our state of dynamic programming is clear. We have current stair, we have jump, and we have did I go back. Okay. Now, if this is clear, okay, guys, what options do I have? First of all, if current stair is equal to more than k plus 2, okay. First of all, let's consider our base conditions, right? Let's have a look. What are our base conditions? Now that we have looked at our state, we need to look at our base conditions and transition. So what are the base conditions, guys? If current stair is greater than equal to k plus 2, we just saw that if it is greater than equal to k plus 2, it is not possible. So in that case, we will return 0. Why will we return 0? Because it is not possible. Otherwise, if current stair is equal to k, does this mean we return 1? No, guys, this is not the case. Why? Because let's say that we are at stair 1, okay, and we need to find the number of ways to reach stair 1. This will return 1, but our answer is actually not 1. Why? Because if we are already at 1, this is one path. But let's say we can go from 1 to 2 and then we can go back to 1. So the answer in this particular case right here is 2. So this won't be a base case, right? If we are at current stair equal to k, we will still try to do the dynamic programming states. Okay, although it is bounded, like this will only work when power is 0. But and either power is 0 or we are at stair k plus 1. Okay, but we still need to consider this. So this won't be a base case, right? I hope you guys understood. This is not a base case. Let me cut this out. So the only base case is if current stair is greater than equal to k plus 2, we return 0. Now, moving on to the transitions. I am at current stair. Let's say I am at dp of current stair. Basically, I'm at a particular stair. I know what is my jump and I know did I go back. Let me name it back. This will either be 0 or 1, right? It will be 1 if I did go back in the previous move, or it will be 0. Jump is going to be a variable and current stair is my current stair. I have two options, either to go back or to go to jump current stair plus 2 raised to jump. Okay. Now, I can only go back, or basically current stair minus 1 only if back is 0. Basically, if in the last move I didn't go back, only then this is valid. So if back is equal to 0, I go to dp of current stair minus 1, right? My jump remains as it is and my back becomes 1, because since I went back, now in this move, my previous step, I did go back. So it becomes 1. Okay. Now, what is my other transition? It is dp of current stair plus 2 raised to jump. We are told that after making this move, okay, let me do this. After making this move, our jump increases by 1. Okay, so jump plus 1 and this becomes 0. Why does this become 0, guys? Because we didn't go back this move. So for the next move, we have the option of going back. These are the true transitions. And what do we return? Our final answer is just this plus this, right? Number of ways to reach k from these moves. This is all that is there in our dynamic programming solution. And also, if current stair is equal to 1, current stair is equal to k, then we will add 1 extra in our answer because we can stop there, right? So this will be plus if current stair is equal to 1. So if basically current stair is k, then we will add a 1 in our answer. Otherwise, we won't count it. Basically saying that if our current stair is k, we could have stopped here, right? So that it is one of the paths and we can just break. So this is our dynamic programming transition and these are our dynamic programming states. I hope this much is clear. If this much is clear, let me show you the code quickly and then I'll prove it to you all. Okay. So since k can be very large, it is 10 raised to 9. I'm using a map because I can't store current step in an array. So map of tuple of long comma int. I wasn't sure if it will overflow. So I have current step, I have is last back, and I have step size. This step size is basically jump, and last is back is it will be 1 if it was so on and so forth, right? Great. So if current step greater than k plus 1 or greater than equal to k plus 2, I return 0. Otherwise, if my dp is set, basically memoizing my dp, if it has already been set, I return that dp, current step, last is back, and step size. Otherwise, my current answer is I have no bounds on going on further, right? So I can already set this. My answer is go to 1 current step plus 2 raised to jump. I set my last is back to 0 and I increase my step size. And of course, if current step is equal to k, I add 1, otherwise I add 0. Okay. Now, if current step not equal to 0 and last is back is false, basically stating that I can go back. So what do? I add current step minus 1, 1 and step size. Basically, I can go back. So I go back. The last move was back. So last is back become 1 and step size remains as it is. In the end, I just return dp of current step, last is back, step size is equal to answer. A very, very simple solution. Okay. It's just a 5-6 line solution. Very, very clean as well. Now, the proof for this. Why does this work? So guys, we are going to take jumps in powers of 2. Let me show you the proof of why this works. Okay. Now, let's say we are going to take some steps, right? So let's say we took all jumps. We took all jumps up till I. Okay. So basically what I'm trying to say is 2 raised to 0 plus 2 raised to 1 plus so on and so forth up to 2 raised to I is around k, right? Is like it's greater than equal to k, let's say. Okay, because we'll be taking some minor steps as well. So this is the number of steps I take. Now the thing to notice is that if I took these many steps, okay, let's say these are the jumps I took: 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3. I can do a back move here I can do a back move in between these two steps. I can do a back move in between these two steps. I can do a back move in between these two steps, and I can do a back move in between these two steps. Okay. So what am I trying to tell you is that for 2 raised to I, before it, we could have done a back move. Before this, we could have done a back move, so on and so forth. We can't do 2 back moves consecutively. So that is basically between 2 jump moves, I can do at most 1. Okay. So what is the number of back moves that I can do? If I am doing 4 jumps, right, then I can do jump plus 1 back moves. Yes or no, guys? Okay. Now, basically 2 raised to 0 plus 2 raised to 1, so on and so forth, up to 2 raised to I minus whatever back moves I did. Let's say I did B number of back moves. This is equal to K, right? And this B right here is in the range 0 to I plus 1 or I plus 2, I must say, right? Yes, this is between I plus 2. Now this right here, guys, this is nothing but 2 raised to I plus 1 minus 1. Okay. This is the formula for summation 2 raised to 0 to 2 raised to I. If you want the intuition to this, let's say I is 3. Okay. So it will be 2 raised to 0 plus 2 raised to 1 plus 2 raised to 2 plus 2 raised to 3. In binary, we can write it as 1, 1, 1, 1. Now this 1, 1, 1, 1 is nothing but 1, 0, 0, 0, 0 minus 1. So it is 2 raised to I plus 1 minus 1. Okay. Minus B is equal to K. So for every position before that, right? 2 raised to I plus 1, 2 raised to I minus 1 minus B is equal to K. Now, if we had taken no amount of back steps, right? Let's consider B is equal to 0, right? This means that 2 raised to I plus 1 is equal to K, around equal to K. So what is I, guys? Log of I plus 1, log 2 of I plus 1 is equal to, wait, sorry for that. Oops. What do? We take log on both sides, right? What does this do? It does I plus 1 is equal to log 2 of K. And we can remove this. So we can say that the number of jumps that we took, okay, the number of jumps is in order of log 2K, okay, where K is 10 raised to 9. So this is around 30, max 30. So if we did no back moves, right? If we did no back moves, then we would have visited 30 unique steps. Okay. Now, if I did one back move, okay, one back move, what can I say, guys? Let's say I visited 1. I visited 1 plus 2, which is 4, which is 3, and then 3 plus 4, which is 7. Okay. Now, if I wanted to do one back move, either if I did the back move over here, then my entire sequence would change to 0 and 2 and 6. Okay. Basically, in the second step, now you can see that we changed the steps that we are going to. Similarly, if I was doing 2 back moves, let's say this was 2, this was 4, and this was 8. So this becomes 1, 3, 7. Okay. If I was doing 2 back moves, then this would have become 0, 2, and 6. you can see that at each position, now we are taking 3 unique values. So if we are doing B back moves, we are at most taking the number of unique pairs that we are forming is at most B into log 2 of K, because the size of this is log 2K, and for each position we can take B unique values. Okay, it's going to be less than that. So the number of steps that we end up visiting, okay, which is basically this right here, this current stair thing, is less than equal to the set or size of current stair set. Okay, this is smaller than equal to B into log 2K. Now B is around 30 and this is also 30. So this is 900. So the current stair is smaller than equal to 900. If you actually go about doing this, okay, this set is smaller than equal to 900, but in reality it is around 600. Okay, but 900 is a good bound. So the time complexity of this becomes very good. What is the time complexity? Okay, how many unique positions can this take? 900. What is the value of jump? It can be up to 30, because 2 raised to 30 is smaller than or equal to 10 raised to 9. And this right here can take the value 0 and 1, so 2. So the time complexity of this is, worst case, it is the number of operations is 900. Let me write it down. The worst case number of moves is 900 into 30 into 2, which is 900 into 60, which is whatever, right? It is 54,000. So we will be using at most these many steps, right? And since we are using a map, we can use a log factor. So into log of this, log of 54000. So the number of operations is very less. It is less than 10 raised to 7, 10 raised to 8. So it passes within time limits. The time complexity of this is O of number of steps, which is, let's say, n step, into number of jumps, into 2, into your log of this thing, right? Now that is more or less it. And the space complexity is again O of n step into jumps into 2, because our for loop here, there is no for loop here. So this works in O of 1. And how many unique are there? It's current step into last is back into step size. That is more or less for this Leetcode discussion, guys. Maybe the proof got a little bit sketchy, but I hope you were able to understand. Thanks a lot for watching. I hope I was able to add some value in your life today. If you understood the problems, do hit the like button. And if you still have any doubts, feel free to reach out to me in the comment section or on LinkedIn or via Discord on TLE Eliminators. Thanks a lot for watching. Bye bye.